Following presentation was made by John Frensley at World's Finest Physics.
In this lesson, we're going to learn about a new type of energy, rotational kinetic energy. The essential question here is going to be how do we use energy principles to explain rotational phenomena. By the end of this lesson, we're going to be able to describe the energy transformations that take place for situations that involve a rotating object, and we're going to be able to apply conservation of energy to a situation in order to calculate an unknown quantity. We have three vocabulary terms that we need to know. First one is rolling, a situation in which an object both translates and rotates while in contact with the surface. Rolling without slipping is a situation where an object can translate and rotate, and the translation and rotation are synchronized so that the atoms of the rolling object do not go against the atoms of the surface in the contact point. And then finally we have rolling with slipping, which is a situation in which an object both translates and rotates, but the translational and rotational are not synchronized, so the atoms of the rolling object move against the atoms of the surface in the contact point. Rotational kinetic energy, because rotation is a form of motion. When atoms move, the atoms have kinetic energy. When all atoms of an object move in the same direction, the object has translational motion, and the kinetic energy of all the moving atoms added together comes to be the translational kinetic energy of the object. The total kinetic energy of the object is 1/2 mv squared. When the atoms of an object move in circles around a line called the axis of rotation, the object has rotational motion, and the kinetic energy of all circling atoms added together sums up the rotational kinetic energy of the object. Translational kinetic energy depends on the translational inertia, which is mass, and the translational speed, velocity, of an object. Rotational kinetic energy depends on the rotational inertia, I, and the rotational speed, omega, of an object. They're like the same thing, right? 1/2 mv squared equals 1/2 I times omega squared. The equation for rotational kinetic energy of an object is going to look like this on your equation sheet. It is possible for an object to have both translational and kinetic energy at the same time. The translational kinetic energy is calculated using the mass and the speed of the object's center of mass. The rotational kinetic energy is calculated using rotational inertia and rotational speed. The total kinetic energy of an object is the sum of translational and rotational kinetic energy. Total kinetic energy equals 1/2 mv squared plus 1/2 I times omega squared. Consider the following situation. A mass m is attached to a string that is wrapped around a pulley wheel. The mass is released from rest, causing the pulley wheel to rotate. The pulley wheel, so we're going to look at three cases. The first one, the wheel has so little mass that it can be considered to have zero rotational inertia. So it's like a frictionless pulley. The pulley wheel has a low rotational inertia, and the pulley wheel has a high rotational inertia. How would the rotational inertia of the wheel affect the falling of the masses? Boom, there you go. Point made. Yellow block is on the left, not attached to anything. It acts as the control in the experiment. The blue wheel has almost no mass and has no rotational inertia. The green wheel has some rotational inertia, and the red wheel has lots of rotational inertia. Harder to get it to rotate. You already knew that the case with lots of rotational inertia, the block was going to be the slowest, and the one with no rotational inertia, the block would be moving fastest. But how can we explain this using energy? As you read the explanations on the following slides, watch the bars carefully. All three systems start with the same amount of gravitational potential energy and no kinetic energy, rotational or translational. The yellow block is in free fall, so all of the gravitational potential energy becomes translational kinetic energy, so the block moves fast as it hits the floor. It's just in free fall. It's being accelerated by 9.8 meters per second every second. Because the blue wheel has zero rotational inertia, all of the gravitational potential energy of the block or its system turns into total kinetic energy of the block. No energy goes to the wheel's rotational kinetic energy because the wheel has such little mass. No rotational inertia, can't have rotational kinetic energy. That means that the blue block falls at the same speed as the yellow block. So they're both just in free fall. What about the green and red? In those cases, gravitational potential energy is transferred into rotational kinetic energy of the wheel. Some of. Not all of it. Right? Because we also have this moving block. So we have the rotating pulley and we have the falling block. The more rotational inertia, the greater share of the energy goes to the wheel's rotational kinetic energy. 1/2 I times omega squared. So even though the speed here is going slow, there is more rotational inertia. The more energy goes to rotational kinetic. The more energy that goes to rotational kinetic energy, the less energy goes back to translational kinetic energy of the block. So think about this as a bucket, and your bucket consists of these 6 blocks of energy that they all start off with. Let's see if I can get it to go again. There we go. If all of the energy goes into the translational kinetic energy, then there's none left over for rotational kinetic energy, which is what happens with the blue. In the green, some of that energy is going to be taken away from our translational kinetic energy and given to the rotational kinetic energy. If we add up all of these blocks, 1, 2, 3, 4, plus 1, 2, we still have 6, the same 6 joules that we started off with, if you want to call it that. Then when we look at the red block, which has a greater moment of inertia, that moment of inertia is stealing more rotational, well, it's stealing more kinetic energy. So the rotation uses up some of that energy. So we're not able to translate. So the block moves slower, taking longer to hit the floor. With what speed does one of the blocks strike the ground? If the block's mass is m and the pulley's wheel mass is big M, radius r, shape constant k, then we can use conservation of energy. The system starts with gravitational potential energy because of the block's height, mgy. System ends with rotational kinetic energy of the wheel and translational kinetic energy of the block. So conservation of energy looks like this. Gravitational potential energy in the beginning equals kinetic energy of the block plus kinetic rotational energy of the pulley. Now we can plug in 2 things. We can use I equals 1/2 mr squared, or I equals whatever the fraction is here, times mr squared. And remember how we said omega equals v over r? Plugging that in. Squares are distributed to each term within the parentheses, the numerator and denominator. Cancel the r squares on the right term, then factor out the v squares and the 1/2. And we get mgy equals 1/2 mv squared plus 1/2 k times big M times v squared. Solving for v, we get that equation, square root of 2 mgy over m plus kn. So what this equation tells us is the higher the k, the higher the shape constant, the farther the atoms are from the axis or the pulley, the higher the big M, this one down here, the slower the block will reach the floor. If little m is really big, or if k or big M are really small, then the denominator just basically becomes little m. And those can cancel out. So what we're left with is v equals square root 2gy, which would be the case if there was no rotational kinetic energy.